It sounds impossible, but NASA just did it. A probe has actually touched the sun, diving into its blazing atmosphere and surviving to send back data that could change everything we know about our star. Here is the English, US, version of your entire text, carefully translated and adapted to maintain clarity, tone, and storytelling style. On April 28, 2021, an extraordinary milestone entered the history of space exploration. It was on that date that NASA's ambitious Parker Solar Probe became the first spacecraft to literally touch the sun. That means it didn't just get close. It actually entered a part of the sun's outer atmosphere known as the solar corona, a place so hot and hostile that many believed getting near it would be impossible without turning to ashes. But the adventure didn't stop there. Fast forward to Christmas Eve 2024, Parker went even further, or better said, even closer. During this historic flyby, it broke its own records for both proximity and speed. Nothing like it had ever been seen before. The probe flew through space around the sun at an astonishing speed of 430,000 miles per hour, 690,000 kilometers per hour. To give you an idea, that's fast enough to circle Earth almost 17 times in just 1 hour. With that, Parker became the fastest human-made object in history. But this achievement was more than just an engineering spectacle. The data collected by the mission is priceless. Every bit of information sent back helps scientists better understand the sun's mysteries, how it releases energy, how it affects space weather, and how its solar winds can impact our satellites and communication networks on Earth. In the coming years, these discoveries are expected to transform our understanding of our closest star. But that brings up a big question. How did Parker get so close to the sun without simply melting? To understand that, we first need to dive into the scorching environment where the probe dared to fly, completing a mission that long seemed impossible. I'm TH, and before we enter this extreme territory, don't forget to subscribe to the channel and activate the bell to receive all updates. Also, click the like button and leave your opinions and suggestions for future videos in the comments. It seems intuitive to think that touching a solid surface, like a planet, and interacting with an atmosphere are two different things. But in the sun's case, that distinction doesn't really apply. I know, it sounds confusing, but let me explain. The sun doesn't have a solid surface because it's not made of solid material. At its core, it's an enormous ball of hot ionized gas, plasma. When we look at the sun, what we see is the photosphere, the layer where the gas is dense enough for photons to escape. This isn't a separate atmosphere resting atop a solid body. It's the solar material itself, gradually transitioning from dense and hot plasma deep inside to a more transparent and less dense state farther out. In stars, the concepts of atmosphere and surface blend into one. There's no solid body hidden beneath an atmospheric shell, as we see on rocky planets. Instead, the solar material thins out gradually as it moves away from the core. The temperature in the photosphere ranges from 4,000 degrees Celsius to 6,500 degrees Celsius. Above that is the chromosphere, which extends about 2,500 kilometers above the photosphere and gets even hotter, reaching up to 30,000 degrees Celsius. And beyond all of these layers lies the corona, the outermost region where Parker plunged. In this region, temperatures soar to between 1 to 3 million degrees Celsius, about 500 times hotter than the surface. This bizarre phenomenon is one of astrophysics' great mysteries. Normally, you'd expect the temperature to drop as you move away from a heat source, like when you back away from a campfire. But with the sun, the opposite happens. Temperature increases as you move from the surface to the outer atmosphere. So, how did Parker survive in a region where temperatures exceed 1 million degrees? That's where thermodynamics comes into play. Imagine opening an oven heated to 200 degrees Celsius. The air inside is extremely hot, but if you quickly put your hand inside without touching anything, you won't burn immediately. That's because air has low density and low heat capacity. It doesn't hold much thermal energy. So the heat transfer to your skin is minimal, and you can endure it for a moment. Now imagine touching a metal tray inside that same oven. Bad idea, it'll burn you instantly. That's because metal has high density and heat capacity, absorbing and transferring much more energy than the surrounding air. This everyday example is similar to what happens in the solar corona. Each particle there moves extremely fast, meaning it's very hot, over 1 million degrees. But because the corona is very low in density, the total heat available for transfer is small. Like the hot air in the oven, it doesn't transfer much heat. That's why Parker wasn't overwhelmed with thermal energy, even while flying through such hot plasma. In practice, Parker's thermal shield heated up to about 100 degrees Celsius, 212 degrees Fahrenheit. While much lower than the corona's temperature, that's still extremely hot, enough to melt most metals on Earth. For example, aluminum melts at 660 degrees Celsius, iron at 1,538 degrees Celsius, and lava flows between 700 and 1,200 degrees Celsius. So Parker survives in an environment hotter than molten lava, almost hot enough to melt iron. To handle this, engineers designed brilliant solutions to protect it from the sun's extreme conditions. 3 major engineering tricks prevented the probe from melting. The first, a heat shield. Parker Solar Probe is equipped with an Advanced Thermal Protection System, TPS. This shield is 2.3 meters, 7.5 feet, wide and about 11.5 centimeters, 4.5 inches, thick. It acts like a giant umbrella, protecting the spacecraft and its delicate instruments from the sun's brutal heat and radiation. Even in the extreme external temperatures, the shield keeps the spacecraft's interior at a comfortable 30 degrees Celsius, 86 degrees Fahrenheit. Made from a carbon-carbon composite, the TPS was chosen for its exceptional heat resistance and low weight. It can withstand temperatures above 2,000 degrees Celsius without melting or degrading. Its core contains a foam layer with many empty spaces, acting as a barrier against heat transfer. The outermost layer is coated with white ceramic to reflect solar energy, improving the shield's efficiency. While most instruments are safely tucked behind the heat shield, 2 vital instruments need to face the sun directly to fulfill their missions. The first is FIELDS, which studies electric and magnetic fields in the solar atmosphere. It uses long, thin antennas, about 2 meters, 6.5 feet, long, that extend beyond the heat shield. These antennas interact directly with charged particles and magnetic fields to collect precise data. Made from titanium and other heat-resistant materials, they're designed to function without active cooling. The second instrument, SPC, Solar Probe Cup, measures the speed, density, and temperature of solar wind particles. It must stay exposed to the wind. Any shield would block the data it's supposed to collect. Built from ultra-heat-resistant metals like tungsten, molybdenum, and niobium, SPC was made to withstand the sun's intense heat without melting. The second major engineering solution involves water cooling, but not just any water. Parker uses deionized water, which is ultra-pure, free from ions and impurities that could cause corrosion or electrical problems. While the main body of the probe stays shielded, the solar panels, essential for generating electricity, must remain exposed to sunlight. Without cooling, they'd overheat and stop working. So the solar panels are fitted with metal cooling tubes filled with pressurized deionized water. This water absorbs excess heat and is pumped to a large radiator located in the shade of the thermal shield. There, the heat is radiated into space as infrared energy. The cooled water returns to the panels, forming a continuous heat transfer loop. The high heat capacity of water makes this system very efficient. The pressurization prevents the water from boiling, even under extreme temperatures. To help regulate temperature, the solar panels are also retractable. They fold inward when the spacecraft is close to the sun, minimizing heat absorption. The third major trick? Sensors. Strategically placed sensors make sure Parker stays perfectly aligned. These sensors sit in the shadow of the heat shield and continuously monitor sunlight exposure. If even a small amount of sunlight is detected, they instantly alert the spacecraft's central computer. Parker then autonomously adjusts its position to keep all instruments in the shade. This real-time autocorrection is crucial for mission safety, since a small error in alignment could ruin everything. Because of the extreme conditions and vast distances involved, real-time human intervention isn't possible. So this automation is key to the mission's integrity and success. Since its launch, Parker has hit numerous milestones. One major discovery came in 2018 when it detected switchbacks, strange, sudden zigzag patterns in the solar wind. These could help explain why the solar corona is so hot and how the wind accelerates through space. Another breakthrough was the discovery of the Alphane surface, a boundary where the sun's gravity no longer controls solar wind particles. Studying this zone helps scientists understand solar wind behavior and its impact on the solar system. Parker also found a dust-free zone around 5.6 million kilometers from the sun. The heat there is so intense that dust particles simply vaporize. This helps scientists understand how dust behaves near stars and how it evolves over time. Another key finding relates to solar energetic particles, tiny bursts of highly charged energy that travel toward Earth. These can disrupt satellites and power grids. By monitoring them closely, Parker helps improve space weather forecasting, so we can prepare before trouble strikes. Finally, Parker captured a 360 degrees view of Venus's dust ring, a belt of particles orbiting the sun along Venus's path. Studying this dust may reveal how it travels and where it comes from. All of this shows that Parker Solar Probe isn't just a machine flying near the sun, it's a symbol of human ingenuity. Every discovery it makes brings us closer to understanding the star that makes life possible. While we can only view the sun from a distance, shielded by our atmosphere, Parker ventured where no spacecraft ever had. It explored invisible layers, measured deadly solar winds, and mapped regions so hot that even dust disintegrates. At its core, this mission is a reminder that even in the face of a powerful star, human curiosity and creativity can overcome the impossible. And Parker's story isn't over. It's still orbiting, still teaching us more about the sun with every pass. There's no doubt that we exist thanks to the sun. But the same star that gives us life also creates an invisible prison, as its immense gravity makes leaving the solar system nearly impossible. But with advancing technology, will we one day escape the sun's grip and explore the galaxy? That's exactly what we explore in the next video. There, we dive into the real challenges of leaving our solar system and the propulsion technologies that might one day allow us to venture beyond our cosmic neighborhood. Hit that subscribe button, share your thoughts below, and let's keep exploring the together. What do you think? Could Trappist we be home to life, or are we chasing a cosmic merge? Thanks for watching, and we'll see you in the next.